Euclidean theory, because then the path integral is slightly better behaved, and of course what our aim is to recover the real-time quantum field theory. Okay? But the Euclidean theory is defined by an integral over the field with an exponential of -1 over h bar times an Euclidean action, which is obtained for the action at real time by a Wick rotation, changing time to imaginary time. And this Euclidean action is just the Euclidean version of the action for the Klein-Gordon field. This is given by this action with a plus, because we are working in Euclidean space. So this is an integral over some Euclidean vector. Let's call it E. So xe belongs to Rd, which is Euclidean space. Okay. And we have seen how you discretize this action in order to define properly by discretizing space and time, and what is the form of this Euclidean action. So we'll discuss that. And the first calculation we did yesterday was to compute the two-point function, which correspond in the functional integral formalism to the expectation value of the products of those two random variables taken at two different points in space-time, which was called G of x1 minus x2. So through symmetry's property, translation invariance, it depends on the distance between the 2 points. So this two-point function is also called the propagator. It's another denomination for that. And we have checked by an explicit calculation that we recover the Feynman propagator of x1 minus x2 in Minkowski space. So M1 d minus 1, so in real time. So indeed, computing this at imaginary time and then making an analytic continuation through Wick rotation, we recover the result of canonical quantization. So at least for the two-point function, the functional integral method is equivalent to canonical quantization. It gives for at least this matrix element the same result. I'm going to discuss it. Okay, so, but we also had seen that on the explicit example, this function of x, let's say, behaves like the absolute value of the vector x to the power 2 minus d at short distance. And therefore, it is singular at short distance. It diverges at when the two fields are located at the same points, when x1 equals x2, so that x is equal to 0. Okay? So that's going to play a very important role in the discussion of quantization, because this is the first origin of what's called ultraviolet divergences in quantum field theory, that I think you have already met in the QFT1 course. So I'm going first to illustrate what the existence of this ultraviolet divergence or this ultraviolet singularities means when you think of the quantum field as defined through a path integral or a functional integral formulation. So what I'm going is, you see, you can view this path integral as a probability distribution. So this is a probability distribution measure on a space of functions. over space. Okay? It's a Gaussian distribution, so it is easy to study because it's the exponential of something which is quadratic in phi, so it's easy to study. And you may ask, what is the geometry of the field configuration for a typical configuration in this functional integral? So of course, this is a random field, so you have to average, but you may ask, what is the typical geometry, the typical shape of a typical field configuration? And this can be studied easily because this is a Gaussian probability, so you can compute it. So I'm going to show you some pictures of how they look like. And first, let me show you, okay, so we have seen that when the dimension of space-time is 1, space-time has only one direction, which corresponds to time. So one-dimensional quantum field theory is nothing but non-relativistic quantum mechanics. You have time, and you have no space connected to time through Lorentz invariance, Poincaré invariance, you see. Of course, quantum mechanics of a system, usually you have a particle in space, but the position of the particle is the value of the field in one dimension. Okay. So this is the field, or the position of the particle. This is time. And these are the several typical histories that gives a contribution for the weight over the 1 when for the propagator between this point and this point. So the classical trajectory is just a straight line. And we have already discussed the fact that in the Euclidean path integral, at Euclidean time, the typical configuration are random walks or Wiener processes. So you take a particle here. According to time, it goes up or down at each steps with some equal probability. And you condition this random process to end up here. Okay. And you see that these are typical, each color line corresponds to a different trajectory. And you see that typically those are continuous. If you follow, for instance, this one, the red one here, which starts there, it goes there, it goes there, it ends up there. You see that typically it's a continuous function, but it's clear that it's very irregular. In fact, that's what I stated. The property of a random walk is that it is a continuous function which has no derivative. Its derivative is infinite everywhere. It's plus or minus infinity. Okay. And this has a precise mathematical definition. So you see, it's a continuous function, but it's irregular in the sense that its derivative is not well defined. It's infinite. Okay, so now let's go back from one dimension to two dimensions. So now I'm looking at how looks like a typical configuration for a field here in two dimensions. So, of course, as we have seen, in order to define this properly, we must first discretize space-time, so take a lattice, and then take the continuum limit. So here I have a two-dimensional lattice. Imagine that here you have a two-dimensional lattice. And this will be a small lattice, so it's 64 by 64. I'm considering a periodic lattice. So in fact, the field configuration here ends up to be the same than here. So we have a field configuration with periodic boundary condition in this direction and in this direction, okay, in both directions. Okay, that's an Euclidean. We have this. The probability distribution is given by this Euclidean weight. So we are doing really probabilities. And of course, what I plot in the third direction is just the value of the field, typical value of the field. So that's one sample in this probability distribution law. Okay? And you see that, of course, since you have a factor h bar, I think h bar is normalized to be 1. Everything is normalized to be 1. I think in this simulation we have settled m to be 0 because M is not important when you study ultraviolet divergences. So it's a quantum massless free field, but that's not very important. Okay? And you see some fluctuation. Of course, there are fluctuations, exactly like for the one-dimensional random walk. This is the analog of a two-dimensional random walk, if you want. Okay. So what's important, it's what's happening when you take the system and keep it to have the same size, but you make the mesh smaller. So I go from a 64 by 64 lattice to a 128 by 128 lattice. But what I have changed is I have divided by 2 the mesh of the lattice, but everything else is fixed. It stays fixed. So the action is the same, and the size of the box is the same. Okay. And then what you see is that it fluctuates, it still fluctuates, but the fluctuations are bigger. So the field is more spiky. And so how is it consistent with the previous picture? You can view this previous picture when you used a coarser mesh by stating that you started from a configuration like this, like this, and you made some coarse graining, exactly like what you have studied in the statistical mechanics course, this coarse graining operation that is at the basis of Wilsonian renormalization group. So when you coarse grain, you average over 4 cells, for instance, you get something which fluctuates less. Okay, so it's further. Now go to a still finer lattice. The field configuration which becomes even more spiky. Okay? So the smaller the scale at which you probe the field configuration, the spikier it is, the more irregular here. And here is the maximum I draw here. And in fact, if you take the continuum limit of this becomes infinitely spiky. And this reflects the fact that at short distance, the fluctuation of the fields becomes larger and larger. That becomes, the smaller the scale length at which you probe the field, the bigger the fluctuation are. So this reflects, just this divergence, reflects the fact that the typical field configuration is infinitely spiky at short distance. Okay? So this is a picture that illustrates this exact mathematical result. Okay? And in fact, mathematicians, when they consider such random field, they can prove easily that they are not function, because not only their derivative is not well defined, but they are not continuous, and in fact, as functions, they are not well defined. In fact, they are defined as random distribution. You know that there are objects that are useful in math, used in physics, which are generalization of functions, which are called distribution. And typical distribution we use in physics is, for instance, the Dirac delta function, which is something which is almost a function because it's not a function only at the origin. But this is a typical example of a distribution that is not a function anywhere, or everywhere it is not a function. It's irregular everywhere. Okay. So this was in 2 dimensions. Now let me play the same game in 3 dimensions. Yes?
Why can we think of the 2-point function as a measure of fluctuation?
Pardon?
Why can we think of a 2-point function as a measure of fluctuation? Because, I mean,
that's
when we did
because what you are measuring are correlation. We are measuring the correlation between this and this. So it's exactly like in statistical mechanics. You see, when you have if you have a random variable, let's say x. Imagine that it's not the position, so I should call it answer. Let me call it phi. if I have a random variable phi, so it's given, it has a probability distribution. As a function of phi, you have some probability distribution. And you can study this probability distribution through its moment. So first, you get the expectation value of phi, which gives you the center of the distribution. Then this is the first cumulant. Then you have the second cumulant, which is this minus this, which tells you what is the typical width of the distribution. And then you have higher order cumulant. Okay? And what you see here is that, of course, in this distribution, phi of x is 0 by parity, but even phi of x squared is infinite. Because if you take the products of a field at the same point, this is infinite. So it means that if you consider the random variable, which is the value of the field just at a single point, it has a probability distribution that has a very, very big tail. So that's its expectation value is infinite. Okay? So it means that it fluctuates a lot.
Yeah, but that's as you said, at the same point.
At the same point, yes. But then,
it's not between configurations at
yeah.
the same point, not on the spatial.
No. So for instance, this is going to measure in somehow how the fluctuation of the field at a given point x1 and at another point x2 are correlated. Because this fluctuates a lot, this fluctuates a lot, this fluctuates less because this is finite. Well, because you see, you can think of it.
X1 not the closest to.
Yeah. So there is a correlation which decays the farther the points are, the smallest this is, because this diverges when you go to large x, so this goes to 0 when you go to small x. So the correlation, there is a decay of the correlation. So the position of the field here at x3 is less correlated to the fluctuation of this one than here. So the fluctuation, each fluctuation independently is infinite, but this infinite fluctuation are still correlated in a finite way. And mathematically, this is perfectly possible. But the closer you go from this point to this point, the more they are correlated. And since the fluctuation here at infinite, this diverge. Okay? Good. So let me go back to this picture. So this is a picture where I did the calculation, studying field configuration for the same theory, but now in 3 dimensions. And of course, in 3 dimensions, it's a bit difficult to represent a field configuration in 3-dimensional space. So I just took a section, a 2-dimensional section. So in fact, I have a quantum field defined on a periodic cube, so a 3-dimensional torus. And I take a 2-dimensional section of this cube, which is a square. And so this is a 2-dimensional section of a typical configuration. And you are going to see the same thing. For a crude mesh, there are fluctuations. For finer mesh, it fluctuates more. It's still much more. And it's even more spiky, you see here. And if you study the correlation, if you start to do statistics and not just showing nice pictures, which of course have been built by a computer, then you see that, remember, in 2 dimensions, the divergence is logarithmic. That's what I wrote here. In 2 dimensions, this is in fact a log, and in 3 dimensions, this is 1 over x. So it means that the higher the dimension, the bigger the fluctuation. The field configuration is more spiky in 3 dimensions than it is in 2 dimensions. So those divergences are stronger, are bigger, as the dimension increases. And that's a very important feature of quantum field theory. It means that the higher the dimension, the wilder field configuration in the path integral are. And this turns out that it will be related to the problem of the fact that constructing a renormalizable quantum field theory becomes a more and more difficult problem the higher the dimension of space-time is. And in fact, for constructing sensible local quantum field theory, d = 4 seems to be the barrier. If you want to construct a theory in higher dimension, it's either very difficult or possible only by extending the quantum theory to non-local field theory, non-local theory. And for instance, the most famous example of a non-local theory which hopefully will describe physics in a higher dimensional space is string theory. String theory is very different from quantum field theory because it's a non-local theory. If you want to define its properties in terms of local degrees of freedom, they are strings which are extended objects. Okay. So I think I am done. Well, I had some other picture, but that's, I don't think I will show them. Okay, so thank you. Can you switch off the, thank you. Okay. So this picture were just for illustrating the meaning of this singularity in the path integral, but I think they are helpful. But of course, looking at a picture doesn't is not an excuse for not doing calculation and thinking about the math. It's just two ways to do. Okay, so now let me go back to the next things I want to do before going to the interacting theory, which is, so we already covered a lot of stuff. Okay, so this is endpoint functions and the Wick theorem. Okay. So I'm going to show you that you recover very easily via the path integral formalism or the functional integral formalism the rule that tells you how to compute higher order correlation function in a quantum field theory. So the endpoint function that I can call this Gn, for instance, so it's defined, it depends on endpoints. Okay, and this is just the expectation value of the products of n field located at n different points, computed with the same action. So this is simply given in a path integral by integral d phi exponential minus 1 over h bar s of phi. This is, of course, well, I'm considering the Euclidean theory, but times this random variable phi of x1, phi of xn, and normalized by the original SE of phi. So that for n equals 0, you get expectation value of the identity random variable, so you get 1. Okay, so this is a general endpoint function. Okay, and in order to compute this, in the functional integral formalism, this is easy. That's easy because this is just what's called an expectation value. This is an expectation value, or an expectation in the language of probability, of a product of Gaussian random variables. Okay? Because the field phi obeys Gaussian statistics. Okay? So, of course, first, if n is odd, this Gn is going to be equal to 0, but just by parity. But if n is even, let's call n equal to m is even, then there is a general theorem for expectation value of products of Gaussian random variable, which is exactly the Wick theorem. And I didn't look exactly in the mathematical literature, but this theorem predates calculation by physicists by a few decades. Of course, it was before people started to think about functional integrals. This was before Feynman. But the result is the same. It's a general property that if you have Gaussian random variable, this product of expectation value of Gn, this Gn, is just going to be the sum of a decomposition in pairs, so in pairings of the random variable, of the product of a pairs, of each pairs, of the two-point correlation function. So that's a very general property of expectation value of products of Gaussian random variable. Okay. So here, the random variable has a value of the field at different points, but this is going to be very general, so for any random variable. So what does this give for, and this theorem is easy to prove. I think there is one tutorial which is doing that. Is it? Or I don't remember. I can. No, okay. I don't remember at some point, but I can show you. Well, I think we can, when starting to discussing the interacting theory, one byproduct of the formalism I'm going to present is to get a proof of this, an easy derivation, right? An easy derivation of this. Okay. So in any case, this formula, that expectation value of products of random variable is given by the sum of products of 2 by 2 point function for each pairs. So you have a products of pair. Let me illustrate that in the case where n equals 4. When n equals 4, you have 4 points, x1, x2, x3, and x4. x2, x3, and x4. And of course, here are the 3 possible different pairings. So you have 3 pairings. Okay, different inequivalent pairings, which means that G4 of x1, x2, x3, x4, where this is a 4-point function, is just the sum of 3 products of 2-point function. And this is g of x1 minus x2, g of x3 minus x4, plus g of x1 minus x3, g of x1 minus x4, plus g of x1 minus x4, g of x2, I'm sorry, x1 minus x3, x2 minus x4, and x2 minus x3. Okay. Because, of course, in this notation, G0, well, G2 is just the propagator, 2-point function. Okay? And if you use this famous Feynman diagrams representation, when you represent the two-point function g of x1 and x2 in position space by just a line joining the point 1 and 2. So these lines represent this function. This means that the 4-point function, so let me write G4 as some object that connects the points 1, 2, 3, 4. This admits just the decomposition, that this is the sum of this diagram, 1, 2, 3, 4, plus this diagram, 1, 2, 3, 4, plus this diagram, 1, 2, 3, 4. So this is a Feynman diagrammatic representation of this combinatorial identity. Okay? Is it clear? So, since the action of the Gaussian free field is quadratic, once you have the two-point function, you have all the correlation of the fields. So, in principle, you should be able to compute everything in the theory, in this quantum theory. And that's, of course, because it's a simple, non-interacting theory. Okay? And now, of course, I stated the Wick theorem for the Euclidean theory, but of course, this extends without any difficulty to the theory at real time, because still it's a Gaussian integral. So this is valid for Euclidean as well as for the theory in real time, in Minkowski space. Okay? Okay, so is there something else that I wanted to discuss? Well, I think that's at that stage all what I wanted to state on the 5-4 theory. Let me just mention something, since I have a few times. Let me mention something. This means that basically, via path integral, we have defined the local phi of x operator and its correlations. Okay, by path integral. We have construct an object which reproduced the field operator that you have constructed by canonical quantization in the QFT1 via creation and elimination operators for modes of the free field. Okay? There is one subtlety, which is that, in fact, now, of course, quantum field theory, like in any quantum theory, you have many more operators which are constructed out of this basic operator by taking products and derivatives of this operator. So, there are objects like composite operator. For instance, the simplest composite operator is phi squared of x. Okay? Yes?
How did we actually define an operator? Do we have like a Hilbert space that works on and everything?
You define an operator through its expectation value. You see?
So you have like
if you know, well, let's go back to the theory at real time. If you know all the expectation value of products of operator between the vacuum state, if you kept this products of operator somewhere here, you can state that this is a product with some in state and some out state, because you construct the quantum state of the theory via the applying field operator on the vacuum. Okay. So if you know all the correlation functions, basically you know all the scalar products of states. And in addition, if you play the same game, right, if you have a product of phi, you see, and you cut it in 3 pieces, you call this in. You call this an operator O. And you call this out. You see? You know all the matrix elements of all the operators. So if you know the correlation functions, you can reconstruct the Hilbert space plus the algebra of operators acting on the Hilbert space. Of course, that's a very, very sketchy presentation. But the idea is that, and there are mathematical theorems that states for what's much more precise, that if you know the correlation function, or if you prefer, if you know the expectation value of observable on states, you can reconstruct the Hilbert space of a quantum theory. So this is equivalent. If you know enough of correlation function, you know the Hilbert space. And if you know the Hilbert space, you know the correlation function. And that's a mathematical theorem. I won't discuss that, but you see, that's the idea. So it's a good question, but here is a very sketchy but answer. But there is a deep mathematical, deep theorems of what's called the theory of operator algebra and of algebraic quantum field theory that tells you when this is possible. So that's the amount of what is called algebraic quantum field theory. Okay, which is a beautiful part of mathematical physics. Okay, good. So in order to go back to this, you have composite operators, and if I want to define what is the operator which corresponds to the products of 2 fields at the same point, I run into a difficulty. Because as we have seen, the expectation value of the products of 2 operators at the same point is infinite. Okay? This is infinite. Okay. However, you can define a composite operator which is called the normal product. Phi squared of x. And which is going to correspond to the normal product operator you have, I think, considered in QFT1, where you express phi in terms of creation and annihilation operator. So phi square is the products of creation, annihilation, and normal products means you put all the creation. I don't remember if it's on the left or on the right. So you put all the creation on one side and annihilation on the other. There is a functional integral version of this normal product, which is the following. I'm going to define this as a limit when I consider the products. I consider the products of 2 operators at 2 different points. And this is an operator that is well defined. But when y goes to 0, it diverges. So let me to subtract to this operator another operator times the divergence. And what I'm going to add to this operator this, which is a function, times an operator which is the identity operator. Identity operator. Okay, and those two are, this is a product of operators. Okay. So you see, this is a linear combination of two operators with a coefficient for the second one, which is a number. And you can check that, in fact, in the series, that's an interesting calculation, that when y goes to x, this exists and is finite. So this means that when you compute expectation value of products of operator, and if you have here insert phi squared of x, this is divergent. But if you insert this new operator, so if you want to compute phi of x1, and somewhere you want to compute phi squared of a point z, and then some other phi of the n of xn. Okay? If you insert this operator, which is the operator, dash phi squared dash of x, of z, let's say. So this is an operator. Okay? This is finite. You have subtracted the divergence which is there. So this is how composite operators are defined. They are defined by normal product prescriptions. So you may, in fact, there is a general theory, you may define products of operator and products of derivative of operators and everything, but you need to take care of the ultraviolet singularities. Something you don't have to do, or almost not have to do in quantum mechanics. In quantum mechanics, defining the operator Q squared is not difficult. Okay. But we're going to meet that again when discussing our normalization. Okay. Okay. So now let me go back to the second big part of this lecture, which is the interacting phi to the 4 theory. I think you have discussed it probably in QFT1, and you have discussed, in fact, you have seen this theory from the point of view of quantum mechanics, of statistical mechanics in the statistical mechanical course, because what I'm going to treat is to treat as a quantum field theory the Landau-Ginzburg-Wilson-Hamiltonian, the model of statistical mechanics described by the Landau-Ginzburg-Wilson effective Hamiltonian, which is the effective low energy action for the Ising model. So this is going to be related to Landau-Ginzburg theory in statistical mechanics. But here I consider it as a quantum field theory. Okay, so why study the phi-4 theory? That's because we have seen the free theory describes a theory of free massless, free massive spinless particles, so free relativistic fermions, Klein-Gordon particle. So when you introduce an interaction, this amounts to have particles, bosons, relativity, that interacts via a repulsive local two-body interaction. And we are going to see why. Okay. So it's a theory that describes a lot of models. Okay. So what is the phi-4 theory? The phi-4 theory is that I start from a model which is described by the action of the free field. D mu phi squared plus m squared over 2 phi squared. So this is, let me write S naught for the free action. This is, of course, an Euclidean. I'm going to consider it in Euclidean framework, so I'm going to omit the E everywhere, but this is an Euclidean theory. Okay, and then I'm counting the interacting theory, which is given by the free action S naught, and I had a term proportional to the integral of a space of the products of phi 4 of x. Okay, and this is, so G is called the coupling constant. Okay, it is going to measure the strength of the interaction. I normalize this by a factor. I divide by a factor 1 over factorial 4. So this 1 over factorial 4, which is 1 over 24, is a normalization factor, which is going to be very convenient. So it just amounts to the definition. And as I explained before, phi squared of x is not something which is well defined. So phi squared, so phi 4, which is ill-defined. So this is to be defined properly. And that's what's going to do in renormalization theory. But for the moment, let's do as if there was no problem. So I consider this as a classical action. So this is a free action. And this is a interacting theory. Okay? And, of course, if now we trust functional integral quantization, we want to construct a functional integral. Okay, so we want to construct subject which is going to be formally an integral over d of phi exponential of minus 1 over h bar s of phi with the interacting theory. Okay. This is for the Euclidean theory. And then we expect to go to Minkowski if everything goes well. So we want to define this. And we want to construct the rule to compute this. Okay? So we want to compute, in fact, if this makes sense, and I'm going to see which measure you are going to take here and which action you are going to take here. If this is defined, if we can define a correlation function, we can define a correlation function for the theory for field operator phi of x1, phi of xn. Okay, so the analog of what we did for the free field, so n points correlation function. That we're going to call Gn of x1, xn by this path integral. So by this object, this ratio integral d phi e minus 1 over h bar s times phi product of phi divided by integral d phi e minus 1 over h bar s with a bit more sketchy notation. And this corresponds, this should correspond by going to Minkowski space to the expectation value, the matrix element between the vacuum of time-ordered products of the products of n fields operators. Okay? where, according to the rule of path integral quantization, this should be the vacuum of the interacting theory. Okay? Which is something different from the vacuum of the free theory. You know, I think you have seen that this is a different state. Omega is different from 0 for the free theory. Well, in fact, if you make this statement to a mathematician, he's going to state you that this state do not live, in fact, in the same Hilbert space. But that's important mathematical subtleties. Okay. Good. So we want to compute this. And so what I'm going to show, well, to derive the path integral, the famous Feynman perturbation theory rules that you have seen, you started to see in QFT1, I think, for diffusion elements. So I'm going to show construct. So we still have more than half hour, so we can start that. So I'm going to introduce some. First, I'm going to introduce some formalism, which is going to be convenient, which is the formalism of what's called generating functionals, which is something you might have seen already in QFT or in statistical mechanics. In fact, generating functions are mathematical. It's a way to gather many mathematical objects in a function. And in fact, this was invented in math by Leonhard Euler, I think so, more than 2 centuries ago, the famous Swiss mathematician, for doing combinatorics of counting, well, precisely, for instance, the number of pairings you have. There is a generating function for this. Okay, so I'm going to define something. Okay. I'm going to define, so let me just take some notation. I start from this path integral that I have not defined very well, but so I'm going to change the action, and for simplicity, I'm not going to change the measure. So I'm going to define a big path integral a bit formally as I integrate over a measure with the measure of the free field. Okay? But then I have exponential of minus 1 over h bar the interacting theory. Okay? And then, okay, that's not the way it is written in the path integral, but I think it's useful. Well, I might not do that. Well, no, okay, let me define the generating function, and after that we are going to that. So I write this, and then I had a term which I'm calling g of phi, where g phi means simply that I introduce a function g of x that multiplies phi of x. Okay? So phi is a random variable. Expectation value of these random variables correspond to matrix element of quantum fields. And this is a function, a classical function. This is a classical function, not random, which is called a source term. Okay? And so you see, if this big integral makes sense, let me call it z. it's a functional of the function g. You see, for each choice of function g, you get a number. So to a function g, you associate a number, which is a value of the functional capital Z. Okay? Good. And out of this object, you can construct the correlation function. Because each time that when you take a functional derivative with respect to g at a function g in something of this function, this gives you a factor h bar minus 1. So let me call this like that. If I take h bar times the functional derivative in the exponential, this makes that there is a phi of x terms that comes out. So this gives a phi of x. So by taking functional derivatives of z of g, you recover correlation functions. Okay, so that's an easy game. Okay, so for instance, let me call an object which is slightly different from the green function. Let me consider what is the functional derivative with respect to z. So let me define the following object. Z bar of x1, xn. Okay, so I'm going to explain why I introduced the z bar here. This is just the result of applying n functional derivative with respect to g at the point x1, xn. So this is going to be h bar to the power n, the functional derivative with respect to g at the point x1, up to the functional derivative of this with respect to the point xn, of the function z of g okay, and for simplicity, I'm going to normalize this by 1 over z naught, when z naught is the path integral for the free theory. So z naught is just integral d0 of phi exponential of minus 1 over h bar as 0 of phi. So this is a partition function for the free theory. Okay. So I define this, and in fact, I take the functional derivative, and at the end, after taking the functional derivative, I set g equal to 0. So you see. So this is just, of course, 1 over z0 times the functional integral d of phi, d0 of phi, exponential of minus 1 over h bar, the action for the interacting theory, times phi of x1 up to phi of xn. Okay, so this is the value of this function, z bar. And it's almost the endpoint green function for the interacting theory. The difference is that at the denominator, we get z0 instead of the partition function for the free theory. You see? The interacting theory. Because here, this is z for the interacting theory, and here this is z0. So in fact, the green function of x1 up to xn for the interacting theory is nothing but this function z bar of x1 xn divided by z bar, let's say, of 0, which is the same function where you have no derivative. So z bar is just the ratio between this z and z0. So this depends on g. This depends on the coupling constant, but this also depends on the coupling components. Because z bar is just integral d0 of phi exponential of minus 1 over h bar s of phi, which depends on phi, normalized by z naught. So z naught disappears between the numerator and the denominator. But that's for convenience. Okay. Okay. So the endpoint Green function in the interacting theory is a ratio of two functional integrals, one containing phi's and one containing no phi. Yes?
D0 phi.
Yeah?
In the definition of z bar, yeah.
I'm sorry? Could you speak a bit louder?
Okay. Yeah, the integration d0 phi.
Yes.
But the action is supposed to be.
I'll take the interacting action which is written there, this one with the phi4 term, but simply, it's a question of normalization, you know. Simply I take the original action for the free theory. Remember, the original action for the free theory was written in a bit sketchy way. This was products over all points in space, the naive interaction d phi of x, and then we had a 2 pi h bar divided by epsilon d minus 2 to the power minus 1/2 or something like that, where epsilon was the mesh of the lattice. When you had defined this path integral through functional realization. So you see, so I take a measure, I do not change the measure by a term involving the mass or the coupling constant. It's just a normalization of the measure. Okay? Yes?
I don't see how are we going to recover in the denominator something that has the interactive measure just by dividing by set r. Because
okay. No, we are not going to recover. We have to incorporate this because this is what I want to compute.
yeah.
Okay. So if I want to compare what's going on with no interaction and what's going on when I plug in the interaction, the numerator and the denominator are changed. Because we change the action both in the functional integral in the numerator and we change the action in the functional integral in the denominator.
Oh.
Okay, so this depends on G, this depends on G. That's what we want to compute. That's a physical quantity, well, physical in the sense that this is a vacuum-to-vacuum matrix element of an operator that corresponds to products of local field operator. So that corresponds to something we need for the physics. And this are normalized slightly differently, so that's less physical, let's say, but we are going to compute this because it's more convenient to compute them and then combine them. Okay. So, and we are going to see also that out of such a functional z of g, we are going to compute other generating functional that correspond to connected diagrams, connected correlation function, and to what's called one particle irreducible functions. This will come out later in the course. Okay, good. So now I will focus on this object, z bar of x. So now z bar of x, to compute z bar of x, I'm going to just use the standard trick of perturbation theory. which consists in assuming that G is small, treat it as if it was a small quantities, and make a series expansion in G. And the obvious series expansion in G consists in, since the action is a sum of the free action plus an exponential, there is somewhere an exponential of G. So think about this definition for Z of G, given by this formula, and separate in the action S into S naught plus the interacting term. Okay? And then you get, of course, that Z bar of x1 up to xn is given by 1 over Z naught times integrating over d phi exponential minus 1 over h bar S naught of phi times exponential minus 1 over h bar the interacting part times phi of x1 xn. So in other words, this is simply the expectation value in the free series of two terms. First, exponential of minus 1 over h bar, G divided by factorial 4, integral over space of phi 4 of x. Okay, that's the first quantity. That's a non-local operator because it involves an exponential and integral. That's a non-local operator times the products of the operator which are local in phi of x1, phi of xn. Okay? And in fact, I think that in the following, since there are x's there, and here I'm going to denote this by z. Okay, so it's just a change of notation. Okay? Just a change of notation. The i's are, let's say, coordinates of what's called external points. Okay? Of course, the zi's, for I equal 1 to n, belongs to Euclidean space. So are vectors in coordinates in Euclidean space. Okay? Good. So these are local operators. And this is a big operator which is not local. Okay.
What does the angle bracket do?
Pardon?
What does the angle bracket do?
Ah, and the angle bracket, I'm sorry, the angle bracket means because I had not finished my calculation. Now I have to perform. So this is before, and now when I integrate over d naught of phi exponential of minus 1 over h bar s naught of phi, what I am computing is the expectation value of this big operator in the free theory. This is an expectation value in the free theory. Okay. So for the moment, I haven't, well, this is exact. I have rewritten the functional integral with a weight proportional to the exponential of the action of the interacting theory as a functional integral of something different weighted by the exponential of the action of the free theory. Okay, so this is exact. This is exact. This is exact. Okay? So now, so this is exact for any value of G. So now, if we assume that G is small, of course, we expand the exponential. We use a Taylor expansion of the exponential. So perturbation means Taylor expand the exponential. And what we get is an expectation value in the free theory of a series of terms involving this. You see? Okay? So we Taylor expand the exponential, so we get a sum. And then we are going to make another things, which seems innocuous. We have a Taylor expansion of a series of terms of order g to the k times something. This theory. And we are going to write this as a sum over k of the term of order g to the k times the expectation value in the free theory 0. We invert. And then what we get is, of course, that this is going to be sum from k equals 0 to infinity of g to the power k minus 1 over h bar factorial to the 4 to the power k, and then integrate. So now I integrate over k points, because when I expand this to the power k, I have k integral. And then I have the expectation value for the free theory of my original field operator, field variables located at the external points times 5,4 at point x1 up to 5,4 at point xk. And I compute the expectation value of this with respect to the free theory. Okay, so if I write this, Taylor expand and invert the expectation value and the series expansion, I get this, which is the basic step, the basic tool to do perturbation theory. Okay. So it seems very simple. Now I must do a warning. This is not at all obvious, because this amounts to make an interversion between taking an expectation value, which means performing a functional integral, and a sum. So this amounts to assume that a functional integral times the sum over k is the same as the sum over k times a functional integral. And when we deal with infinite sums, in both cases these are infinite sums. Interverting infinite sums is not obvious in mathematics. Warnings, interversions of infinite sums is not obvious. Okay, so there are some important subtleties associated to this interversion. For instance, one subtlety is that this original sum defines an analytic function. An exponential is analytic. So this defines an entire function in G. When you intervert, this defines a function which has not entire, it has not an infinite radius of convergence, but it even has no radius of convergence. It's an asymptotic series only. In G, but it's not a series that is convergent in the sense of analytic function. Okay. Only. I'm not going to discuss that. But you have to keep this in mind. This operation is something mathematically highly non-trivial. Okay. Okay, so now we have this. So if we trust what we did, we can re-express the numerator and the denominator, because if we have no external points, we have the denominator, as a series expansion in powers of G that involves integration over what's called now internal points of expectation value for the free theory of products of operator, some associated to the external points and some associated to the internal points. And the internal points we integrate over their position. Okay? Is it clear? Okay. So now, of course, Feynman diagrams appear when you apply Wick theorem. When we re-express this as a sum over pairings of products of propagators. So expectation value for the free theory between some points and some points, where this is the propagator of the free theory. And the points here may be x's or z's. Okay. And that's the kind of perturbation theory that I think you have met already in the previous courses. So here I'm just going to show the systematics of the kind of perturbation theory and calculation in terms of Feynman diagram that you have most probably already met. And the amounts of this object, you see, this big object is called a Feynman. So, I'm sorry, first, to each pairing is associated a diagram. A Feynman diagram obtained by just representing each propagator by a line. Things what I did, what I did just there. So we have a Feynman diagram, and to a Feynman diagram is associated a function, and when we integrate, you get a Feynman integral associated to each diagram, and I'm going to give you example. Okay? So, I'm going to give the rules. So first, you see, the Feynman rules are the following. Rules. I'm going to write that for the Euclidean theory. For the Minkowski theory, you have to take into account the I factors, but so I'm going to write them for the Euclidean theory. So you see, first you have phi and phi squared. So to an external points, you see, hi. This is an external point. I associate what's called an external vertex. So a vertex that is located at the position zi. To an interaction term of phi to the 4, I associate what's called an internal vertex. I'm going to represent it by a field point. And it has 4 legs. And it's associated to some x, g. Okay? So I goes from 1 to n, where g, the index g, goes from 1 to k. So they depend on the order of perturbation. So internal vertex, external vertices have just 1 leg attached to them, and internal vertices have 4 legs. 1 leg, if you want, 4 legs. Okay? And okay, to each vertex is associated just a factor 1 to each external vertex, and to each internal vertex is associated factor, this factor, minus g divided by h bar. So I get a factor minus g divided by h bar factor. while here I have just a 1 factor. With my choice of notation, there is no factor associated to this one. And of course, the rule is that now I'm going to have propagator, and the propagator in the theory is just represented by a line joining 2 points. The points may be z or x, so let me call this y1 and y2, because it can be either a z or an x. And the propagator is just the propagator of the free theory. The free theory is given by the action of the free theory. So the free propagator is just h bar times the Fourier transform d dk over 2 pi d e I k. This is a 4 vector k times y1 minus y2 divided by k squared plus m squared. Okay, so this is a propagator, and there is factor h bar because that corresponds to the product expectation value of 2 fields, and in the action there is a 1 over h bar. So I'm going to write this as h bar times something that I'm going to call g0, which is z0 of y1 minus y2. So this is a green function that doesn't depend on h bar. Okay, so I'm keeping the h bar because there is some interesting feature emerging when you take into account the h bar. So this is a propagator, this is the external vertex, this is internal vertex, and the rule is that you integrate over the internal vertex positions. Because here you have an integration, so you have to perform an integral over d dxg for each vertex. Okay? Good. And so these are the Feynman rules in position space. And I'm going to discuss a bit later Feynman rules in momentum space that are the one I think you have mostly discussed in QFT1. Okay. Just obtained by Fourier transforming everything. Okay, so once you have that, let me just consider. So first, let me consider the 0-point function. So I'm considering the case where n equals 0. So the perturbative expansion of this denominator. Okay? So what is the first term? I have no n, so of course, at order 0, I get a factor 1. I get g0, everything at power 0. So at order k equals 0, I just get a factor 1. Okay. At first order, what I have to compute is either factor minus g divided by 1 over factorial 4 h bar. And I have to compute the integral over x1 of the expectation value of y4 of x1 in the free theory. Okay? Now, Wick theorem. This is given by the sum of the three contraction between 4 fields which are located at the same point. So this gives the same contribution. This gives simply minus 1 over g, minus g over h bar, and then I get 3 contribution divided by factorial 4, which is 24. So I get 1 over 8, okay? And then I get integral dd of x1 of phi squared of x1 minus x1. So that's phi squared of 0, if you prefer, because you can translate in the end, squared. Okay? Which correspond in Feynman diagrammatic representation into having a factor minus g over 8. There is 1 over h bar, but there is 2 h bar in the propagator, so I get a factor h bar, if I'm not mistaken. And then I have the contribution of this diagram. So I have 2 phi squared. So I represent each expectation of phi squared by 1 diagram, like that. It's located at the point x1. And remember, my rule is that I integrate over x1, so implicitly in this representation, I integrate over the position of this vertex because it's an internal vertex. Okay? So this is the Feynman diagram associated to this. Okay. Okay. So the amplitude associated to this diagram is just the product of the 2 g naught of 0. So the amplitudes of this diagram is just with my notation is just g naught of 0 squared. Okay. So, of course, and if you like, each g naught of 0 is the amplitude associated to this single diagram, which is called a tadpole diagram for some, because you may think of it of this having 2 little legs and it's a tadpole. And of course, it is infinite, this number we have seen. But let us close our eyes for the moment and assume that the theory is, for instance, on the lattice. In these rules, nothing depends exactly of whether the theory is on the lattice, what is the form of the propagator. So, okay. Okay. So now, let me just state the result at order k equal 2. So at order k equal 2, oh, there is a very important mistake here. There is, of course, a 1 over factorial k, because I'm expanding the exponential. I forgot this. Okay. So let me just end up. At order k equal 2, what I get is a factor g squared 1 over factorial 2 times 1 over factorial 4 squared, 1 over h bar squared, and I have an integral with 2 points, and an expectation value of phi 4 at point x1 and phi 4 at point x2. Okay? So, applying Wick's theorem is going to give a more complicated, many more contribution. I'm just going to draw the diagram that is going to appear, and we'll discuss them later next Monday. You have diagrams like that with the point 1 and the point 2. You have a diagram like that, 1 and the point 2. And we have a diagram like that. So you may have no propagator joining vertices 1 and 2, 2 propagators joining vertices 1 and 2, or 4 propagators joining vertex 1 and 2. And these are going to have a G factor. These are going to have H bar factor. So these are going to be G squared H bar squared. And if we apply Wick's theorem, I think you get that this is factor 1 over 120 height. This is going to have a factor 1 over 216. And this is going to have a factor 1 over well, factorial 4. Factorial 4 is 24, 1 over 48. Okay, but I'm going to explain that later. Okay, so let's end the lecture here. And next time we are going to continue this and to see the structure of perturbation theory for the other point n2 and 4-point functions that are very important. And I start to discuss the systematic of this. Okay, thank you.